Bond villain layers to Superman's fortress of Solitude, ice bases have always captured our imagination. But what Hollywood got wrong was thinking they were impossible to build. In reality, by 1960, the U.S. Army had begun Camp Century, a 3-kilometer pilot test under the ice housing 200 men beneath Greenland's ice cap. The official story, scientific research. The truth. Camp Century was just the beginning of a plan so audacious it could have changed the Cold War forever. The full Project ICEWORM envisioned a 130,000 square kilometer complex, 3 times larger than Denmark. Now, with 2025 bringing unprecedented Arctic military activity, with Russia and China modernizing ice bases again, this buried secret is more relevant than ever. The scale of what America actually planned was staggering. The nuclear-powered city under ice. What the Army envisioned was an underground city stretching across an area 3 times larger than Denmark, carved directly into the Greenland Ice Cap. Not some modest research station, but a sprawling metropolis designed to house 11,000 military personnel in 4,000 kilometers of interconnected tunnels. Project ICEWORM represented the most ambitious construction project ever attempted in polar conditions, dwarfing anything built before or since in the Arctic. The Army's vision went far beyond a simple military base. They planned to create a complete self-sustaining civilization beneath the ice, complete with residential quarters, dining facilities, recreation centers, medical clinics, and workshops. The underground city would feature its own power grid, water treatment systems, waste management facilities, and communication networks. Engineers designed living spaces that could accommodate families, complete with schools for children and shopping areas for daily necessities. The facility would include theaters for entertainment, gyms for fitness, and even churches for worship services. Creating such a massive installation in one of Earth's most hostile environments required revolutionary engineering approaches. The temperature regularly dropped to minus 40 degrees Celsius, with howling winds that could reach 200 kilometers per hour. The ice cap itself presented unique challenges, constantly shifting and moving under its own immense weight. Traditional construction methods would prove useless in these conditions, forcing engineers to develop entirely new techniques for excavation, construction, and maintenance in frozen environments. The power requirements for this underground metropolis demanded an unprecedented solution. Diesel generators could never supply the massive energy needs of 11,000 residents and their equipment. The Army decided to install a portable nuclear reactor specifically designed for Arctic conditions. The PM-2A reactor would generate enough electricity to power a medium-sized city, providing heating, lighting, and power for all the sophisticated equipment needed to maintain operation. This reactor represented cutting-edge technology, engineered to operate reliably in extreme cold while providing continuous power for years without refueling. Construction techniques had to be invented from scratch. Engineers developed specialized snow removal equipment capable of carving through hundreds of tons of packed ice per hour. They designed prefabricated tunnel sections that could be assembled in Arctic conditions, using materials that wouldn't become brittle in extreme cold. The tunnels themselves required innovative arch designs to distribute the enormous weight of ice above, while flexible joints allowed for natural ice movement without structural failure. The project operated under extraordinary secrecy measures. Officially, the Army described their work as peaceful scientific research into Arctic construction methods and climate studies. They established Camp Century as a smaller demonstration facility, housing just 200 personnel to test construction techniques and living conditions. The public story emphasized international cooperation and scientific advancement, with researchers from multiple countries participating in studies of ice core samples and weather patterns. Behind this peaceful facade lay a military purpose so significant it justified spending billions of dollars in 1960s money. Greenland's strategic position provided unprecedented advantages for nuclear operations. Located between the United States and Soviet Union, missiles launched from the ice cap could reach Moscow faster than weapons fired from American soil. The massive ice sheet offered natural camouflage that would make detection virtually impossible, even with advanced reconnaissance satellites. The extreme environment itself provided protection, as few Soviet agents could operate effectively in Arctic conditions for extended periods. The true purpose of Project ICEWORM involved creating the ultimate hidden fortress for America's most powerful weapons. The underground city would serve as a mobile missile base, constantly shuffling nuclear weapons between different launch sites to prevent Soviet targeting. The facility would house hundreds of specially modified intercontinental ballistic missiles, each capable of delivering multi-megaton warheads to targets across the Soviet Union. Command and control systems, buried deep in the ice, would coordinate launches and maintain communication with Pentagon leadership. The defensive advantages were equally impressive. The massive ice cap provided natural armor several hundred meters thick, requiring direct hits from the most powerful nuclear weapons to penetrate. The distributed tunnel system meant that even multiple nuclear strikes couldn't destroy the entire facility. Soviet war planners would need to target thousands of potential launch sites scattered across an area larger than most European countries, requiring them to expend their entire nuclear arsenal just to attempt eliminating this single installation. Intelligence estimates suggested the Soviets would need over 3,000 nuclear missiles to guarantee destruction of the ICEWORM complex, far more than their existing arsenal could provide. This created an impossible strategic equation where attacking the facility would consume so many Soviet weapons that they couldn't simultaneously target American cities and military bases. The underground city would survive any conceivable first strike, while retaining the ability to devastate the Soviet Union in retaliation. But understanding why the Pentagon was willing to invest so heavily in this frozen fortress requires examining the nuclear predicament that haunted military planners throughout the 1950s. Cold War nuclear strategy revolution. The nuclear age created a terrifying vulnerability that transformed military strategy. America's growing arsenal of atomic weapons sat exposed at known locations, making them perfect targets for a Soviet first strike. Strategic Air Command bases housing nuclear bombers were clearly marked on maps and easily identified from satellite reconnaissance. The massive B-52 stratofortresses required long runways and extensive ground support facilities that couldn't be hidden or disguised. Enemy planners knew exactly where to aim their own nuclear weapons to eliminate American striking power before it could respond. The situation grew worse as both superpowers developed intercontinental ballistic missiles. The first generation of American ICBMs like Atlas and Titan required enormous launch complexes with above-ground fuel storage tanks, guidance systems, and support buildings. These installations were visible from space and took hours to prepare for launch. Soviet reconnaissance satellites could easily count American missiles and target each installation individually. The Jupiter and Thor medium-range ballistic missiles presented even greater vulnerabilities. Stationed at exposed bases in Turkey, Italy, and Britain, where they served as obvious targets for Soviet retaliation. These shorter-range missiles created additional strategic problems because they needed positioning close to Soviet borders to reach their targets. The Jupiter missiles in Turkey could strike Moscow in just 10 minutes, making them incredibly threatening to Soviet leadership, but equally vulnerable to conventional attacks or sabotage. The weapons required large crews for maintenance and operation, complex ground support equipment, and regular fuel deliveries that made concealment impossible. Any conflict would likely begin with coordinated strikes against these exposed installations, eliminating much of America's nuclear capability before the weapons could be used. The Cuban Missile Crisis demonstrated just how dangerous this vulnerability had become. Soviet medium-range missiles in Cuba could have destroyed strategic air command bases across the southeastern United States within minutes of launch. The crisis revealed that both superpowers had created nuclear forces that were powerful but fragile, capable of devastating attacks, but unable to survive an enemy first strike. Military analysts calculated that a coordinated Soviet attack could eliminate 80% of American nuclear forces before they could respond, leaving the United States defenseless against follow-up strikes on cities and industrial centers. Pentagon strategists explored various solutions to protect American nuclear forces from surprise attack. Operation Chrome Dome kept nuclear-armed B-52 bombers airborne around the clock, ensuring that some weapons would survive any ground attack. These airborne alert missions required enormous resources and created constant safety risks. including several accidents that nearly triggered nuclear detonation. The program consumed vast amounts of fuel and required hundreds of aircrews to maintain continuous coverage, making it extremely expensive and difficult to sustain long-term. Engineers developed hardened missile silos designed to withstand nuclear attacks, burying Minuteman ICBMs in reinforced concrete bunkers scattered across the American Midwest. These underground installations provided better protection than surface facilities, but remained vulnerable to direct hits from accurate Soviet warheads. The silos' fixed locations meant that enemy planners could target each installation individually with multiple warheads to ensure destruction. Satellite reconnaissance made it impossible to hide new silo construction, giving the Soviets complete knowledge of American missile locations and quantity. Military planners began considering more radical approaches to the survivability problem. What if nuclear weapons could be hidden in locations so remote and inhospitable that enemies would never think to look for them? The concept required finding terrain that provided natural camouflage while remaining accessible to American forces, but not Soviet reconnaissance. The location would need to support large-scale military operations while maintaining complete secrecy from enemy intelligence services. Greenland emerged as the perfect solution to America's nuclear vulnerability crisis. The massive ice sheet covered 1.7 million square kilometers, providing unlimited space for concealed installations. The island's position between North America and Europe placed it closer to Soviet targets than missile bases in the continental United States, reducing flight times and increasing accuracy. Denmark had granted the United States military access rights during World War II, giving American forces legal authority to operate on Greenlandic territory without requiring additional negotiations. The ice cap offered natural advantages that no other location could match. Satellite reconnaissance would see only unbroken white expanses with no visible signs of military activity. The extreme climate deterred Soviet intelligence operations and made infiltration by enemy agents nearly impossible. The constantly shifting snow would bury any surface traces of construction within months, creating perfect camouflage that renewed itself automatically. Enemy planners would face the impossible task of targeting weapons they couldn't locate or even confirm existed. Traditional missile silos concentrated nuclear weapons in predictable patterns that simplified enemy targeting calculations. An ice-based installation could scatter launch sites across thousands of square kilometers, forcing Soviet planners to allocate multiple warheads for each potential location. The mobile nature of ice tunnel systems meant that missiles could be moved regularly between different launch points, making accurate targeting impossible even with perfect intelligence. The strategic mathematics were compelling for American war planners. A hidden ice base would shift the strategic balance by creating an undetectable nuclear arsenal that could survive any first strike. But creating such a revolutionary weapons system would require missiles specifically designed for the unique challenges of Arctic deployment. The Iceman missiles, developing weapons for these conditions, demanded completely new engineering approaches. The Army needed missiles specifically engineered for Arctic deployment and mobile operations. Standard ICBMs like the Atlas and Titan required massive launch complexes with above-ground fuel systems that would freeze solid in Greenland temperature. The propellants used in conventional missiles turned into useless slush at -40 degrees Celsius, while electronic components failed when exposed to extreme cold and constant moisture from melting ice. The solution emerged from Chrysler Corporation's missile division, which developed specialized weapons designated as Iceman missiles. These weren't entirely new designs, but heavily modified versions of the Minuteman ICBM, redesigned from the ground up for Arctic conditions. Engineers replaced standard fuel systems with solid propellants that remained stable in extreme cold, while new heating systems kept critical components at operational temperature. The missile bodies received special coatings to prevent ice buildup on control surfaces, and guidance systems incorporated Arctic-specific navigation corrections to account for magnetic field variations near the North Pole. Each Iceman missile carried a single thermonuclear warhead with a yield of 2.3 megatons, roughly 150 times more powerful than the bomb dropped on Hiroshima. The weapons measured 18 meters in length and weighed approximately 35 tons when fully fueled and armed. Their range extended to 5,000 kilometers, sufficient to reach any target within the Soviet Union from Greenland launch sites. The warheads incorporated the latest fusion bomb technology, using lithium deuteride as fusion fuel and a plutonium fission trigger to achieve maximum destructive yield while maintaining compact dimensions suitable for ICBM delivery. The revolutionary aspect of the Iceman system wasn't the missiles themselves, but their deployment concept. Rather than fixed silos, the weapons would operate from a mobile rail network that could shuffle missiles between launch sites to prevent Soviet targeting. Military planners designed a system using 600 missiles distributed among 2,100 potential launch positions scattered across the ice cap. The missiles would move constantly between different locations, with Soviet intelligence never knowing which sites actually contained active weapons versus empty decoys. Rail lines would crisscross the ice cap in a grid pattern covering the massive area. The network required over 4,000 kilometers of track, constructed using special steel alloys that remained flexible in extreme cold. Mobile launch cars would transport missiles between different tunnel sections, stopping at hardened launch silos that could be activated within minutes of receiving fire orders. The entire system operated like a massive shell game, with weapons constantly relocating to prevent enemy forces from developing accurate targeting information. This mobile deployment created a psychological warfare advantage that went beyond simple camouflage. Soviet war planners would face an impossible calculation when trying to eliminate the Iceman threat. Intelligence services might identify 2,100 potential launch sites, but would never know which ones contained actual missiles at any given time. The constant movement meant that targeting information became outdated within hours, forcing Soviet forces to attack far more sites than necessary to ensure hitting mobile weapons that might have already relocated. The technical challenges of maintaining missiles in Arctic conditions required numerous engineering innovations. Each launch site needed heating systems to keep weapons at operational temperatures, while moisture control systems prevented ice formation on critical components. Maintenance crews would work in underground facilities connected to the tunnel network, performing regular inspections and repairs without exposing missiles to surface conditions. Special transport vehicles would carry replacement parts and technicians throughout the tunnel system, maintaining operational readiness across the entire network. Command and control systems for coordinating 600 mobile missiles required technology that pushed the limits of 1960s capabilities. Underground command centers would track the location of every missile in real time, maintaining communication with mobile launch crews and Pentagon leadership. The system needed redundant communication links to ensure that launch orders could reach weapons even if primary communication lines were damaged by enemy action. Computer systems would calculate optimal launch sequences and target assignments, accounting for missile locations and flight paths to maximize destructive effectiveness. The coordination complexity was staggering. Launch commanders would need to track which sites contained missiles, which were empty decoys, and which were undergoing maintenance or relocation. The system required precise timing to ensure that missiles didn't collide during simultaneous launches from nearby sites. Weather monitoring systems would track wind patterns and visibility conditions that could affect launch operations, while navigation systems would provide updated targeting coordinates accounting for ice movement and magnetic field variation. The strategic mathematics worked heavily in America's favor. Soviet forces would need to attack thousands of potential launch sites to ensure eliminating the mobile missile threat. Intelligence estimates suggested that neutralizing the Iceman system would require over 3,500 Soviet nuclear warheads, far exceeding their existing arsenal. This created an impossible strategic equation where attacking Greenland would consume so many Soviet weapons that they couldn't simultaneously target American cities and military installations. The mobile launch system would have fundamentally altered Cold War nuclear dynamics by creating an undetectable and essentially invulnerable nuclear force. But first, The Army had to prove that such an ambitious underground complex could actually be built in one of Earth's most hostile environments. Building the impossible. Camp Century became the testing ground where theory met Arctic reality. Carving a massive underground complex through solid glacier ice sounds like something from a fever dream, but Army engineers approached this challenge with methodical precision. The Greenland Ice Cap presented conditions unlike anything encountered in conventional construction projects. Temperatures regularly dropped to -57 degrees Celsius, while howling winds reached speeds that could knock grown men off their feet. The ice itself wasn't uniform, but contained layers of different densities, air pockets, and hidden crevasses that could swallow entire vehicles without warning. The Army developed specialized excavation equipment specifically for ice removal operations. The Swiss-manufactured Peter Snowmiller became the workhorse of tunnel construction, capable of chewing through 120 cubic meters of packed snow and ice per hour. This massive machine operated like a mechanical beast, with rotating cutting heads that pulverized ice into manageable chunks while conveyor systems transported debris away from work area. The miller required constant maintenance in Arctic conditions, with crews working around the clock to prevent hydraulic fluid from freezing and metal components from becoming brittle in extreme cold. Construction crews discovered that traditional building techniques were useless in ice environments. Standard concrete cracked immediately when exposed to temperature fluctuations, while steel became so brittle it shattered under normal working loads. Engineers developed innovative arch-shaped tunnel designs that distributed the enormous weight of ice overhead while allowing for natural expansion and contraction. The tunnels measured 8 meters wide and 4 meters high, providing adequate space for vehicle traffic and equipment installation, while maintaining structural integrity under hundreds of tons of ice pressure. The sealing systems required revolutionary approaches to prevent collapse while allowing for ice movement. Engineers installed corrugated metal panels that could flex with natural ice shifts without losing structural strength. These panels were heated continuously to prevent ice buildup that could add dangerous weight loads. Insulation systems kept interior temperatures comfortable for personnel while preventing heat loss that could destabilize surrounding ice formation. Getting construction materials and equipment to work sites hundreds of kilometers from the nearest port created logistical nightmares that tested military planning capabilities. Every piece of equipment, every construction component, and every supply item had to be transported across the ice cap using specialized vehicles designed for Arctic conditions. The Army established Camp Tudo as a coastal staging area where ships could unload cargo during the brief summer months when ice conditions permitted maritime access. The supply system relied on heavy sled trains pulled by massive tracked vehicles that could navigate across ice fields carrying enormous loads. These convoys operated like Arctic freight trains, with multiple cargo sleds connected in sequences that stretched for hundreds of meters. The tracked vehicles consumed enormous quantities of fuel while battling through snowdrifts and around crevasses that appeared without warning. Working conditions challenged every aspect of conventional construction practices. Metal tools became so cold they could freeze to exposed skin within seconds, requiring workers to wear special gloves and use heated tool storage systems. Welding operations required enclosed heating tents to prevent metal from cooling too rapidly and developing stress fracture. Electronic equipment failed regularly when moisture condensed on circuit boards and froze into ice crystals that caused short circuits and component failure. The extreme temperatures created constant equipment failures that slowed construction progress. Hydraulic systems required special Arctic-grade fluids that remained liquid at -40 degrees, while engines needed continuous heating to prevent fuel lines from freezing. Battery-powered equipment lost most of its capacity in cold conditions, requiring heated storage areas and frequent recharging cycles. Supporting thousands of personnel in such hostile conditions required sophisticated life support systems that went far beyond basic heating and shelter. The underground facility needed massive ventilation systems to provide fresh air while removing carbon dioxide and moisture that could create dangerous conditions. Water supply presented unique challenges since conventional wells were impossible in frozen ground. Engineers developed the Rodriguez well system, which used heated probes to melt ice and create water sources directly from the glacier itself. Power generation for such a massive facility eliminated conventional diesel generators as practical options. The fuel requirements alone would have demanded constant supply convoys that were vulnerable to weather disruptions. The nuclear reactor solution provided reliable power generation that could operate continuously without fuel resupply, while generating enough electricity to support heating, lighting, and equipment operations for thousands of personnel. The PM-2A reactor represented cutting-edge portable nuclear technology designed specifically for remote installations. The reactor core contained 20 kilograms of highly enriched uranium that could generate 2 megawatts of continuous electrical power for years without refueling. The entire reactor system weighed 400 tons and required specialized transportation equipment to move components across the ice cap to installation site. Camp Century proved that large-scale ice construction was not only feasible, but could create surprisingly comfortable living conditions in the world's most hostile environment. The demonstration facility successfully housed 200 personnel year-round while maintaining all necessary life support systems and operational capabilities. What the engineers had accomplished beneath the ice exceeded even their own expectations for what was possible in such extreme condition. Life in the Ice City. The residents who called this frozen world home discovered that life beneath the ice could be surprisingly comfortable. Walking into Camp Century felt less like entering a military installation and more like stepping into a small American town that happened to be buried under tons of ice. Personnel enjoyed hot showers with unlimited water, a luxury that seemed impossible in an environment where everything else froze solid within minutes. The recreation center housed a proper movie theater with comfortable seating where residents could watch the latest Hollywood films shipped in from the United States. A well-stocked library provided books, magazines, and newspapers that kept personnel connected to the outside world. The base included a fully equipped barber shop where military personnel could maintain grooming standards despite being hundreds of kilometers from civilization. A chapel provided space for religious services and quiet reflection, complete with an organ and religious texts from multiple denominations. The post exchange operated like a small department store, stocking everything from toiletries and clothing to candy and cigarette. Personnel could purchase personal items using military script, creating a sense of normalcy in an otherwise surreal environment. Daily routines followed patterns similar to conventional military bases, with reveille, meals, work assignments, and evening recreation periods. The 200 residents developed their own social dynamics and traditions, including adopting Mukluk, a sled dog who became the unofficial base mascot. Mukluk wandered freely through the tunnels, providing companionship and entertainment for personnel who missed pets and families back home. The dog adapted remarkably well to underground life, becoming a beloved fixture who lifted morale during the long, dark months of Arctic winter. Living buried under kilometers of ice created psychological pressures that military psychiatrists had never encountered before. Personnel dealt with claustrophobia from spending months in narrow tunnels without seeing natural sunlight or breathing fresh outdoor air. The constant artificial lighting disrupted normal sleep patterns, while the unchanging underground environment eliminated natural time markers that helped regulate human biological rhythm. Some residents experienced depression and anxiety from the isolation, leading to the establishment of regular counseling sessions and recreational activities designed to maintain mental health. The dining facilities served meals that rivaled restaurants in major American cities, with fresh ingredients flown in regularly during favorable weather conditions. Kitchen staff prepared elaborate meals using ingredients stored in massive refrigeration systems that took advantage of the natural cold environment. The dining hall became a social center where personnel gathered to share news, discuss work assignments, and maintain the social connections essential for psychological well-being in such isolated conditions. Scientific research activities provided legitimate cover for the military mission while conducting genuinely valuable studies of Arctic conditions. Researchers collected ice core samples that revealed climate patterns spanning thousands of years, while meteorologists gathered weather data that improved understanding of Arctic atmospheric conditions. Glaciologists studied ice movement and formation processes, while biologists examined how plants and animals adapted to extreme cold environments. These research programs attracted international attention and provided credible explanations for the facility's existence without revealing its true military purpose. Maintenance operations consumed enormous resources and required constant attention to prevent system failures that could endanger personnel safety. Heating systems needed continuous monitoring to ensure proper operation, while ventilation equipment required regular cleaning to prevent ice buildup that could block airflow. Electrical systems demanded frequent inspection and repair due to moisture damage and temperature fluctuations that stressed components beyond normal operating limit. Communication systems connected Camp Century to military headquarters through multiple redundant channels, using radio equipment that operated on different frequencies to ensure reliable contact despite atmospheric interference common in polar regions. Recreation programs addressed the psychological needs of personnel confined underground for extended periods. The facility organized sports leagues, hobby clubs, and educational classes that provided mental stimulation and social interaction. Game rooms featured pool tables, card tables, and board games that offered entertainment during off-duty hours. Musical instruments and audio equipment allowed personnel to enjoy music and organize informal concerts that built community spirit among the isolated residents. Workshop areas maintained skilled technicians who repaired equipment and manufactured replacement parts that couldn't be easily shipped from outside suppliers. Machine shops operated lathes, mills, and welding equipment needed to fabricate custom components, while electrical workshops handled repairs to communication and electronic systems. Vehicle maintenance bays serviced the tracked vehicles and generators essential for surface operation. Camp Century successfully proved that substantial numbers of military personnel could live and work effectively in underground Arctic installations throughout the year. Personnel maintained high morale and operational effectiveness despite the isolation and extreme conditions, validating the concept for much larger installations planned under Project ICEWORM. The demonstration showed that an underground Arctic city housing thousands of military personnel was not only possible, but could provide living standards comparable to conventional military bases in temperate climates. But creating this comfortable underground world required solving one critical challenge that would prove far more dangerous than anyone anticipated. The massive power requirements for heating, lighting, and life support systems demanded an energy source that could operate reliably in the world's most hostile environment. The nuclear reactor nightmare. The Army chose the PM-2A reactor as their solution, a cutting-edge portable nuclear system designed specifically for remote military installations. The compact reactor contained 20 kilograms of highly enriched uranium fuel that could generate 2 megawatts of continuous electrical power, enough to supply a small city with electricity for years without refueling. The reactor core measured just 1.2 meters in diameter and 1.8 meters in height, making it significantly smaller than conventional power plant reactors, while maintaining impressive power output capabilities. Moving 400 tons of reactor components across the Greenland Ice Cap created transportation nightmares that pushed Arctic logistics to their limits. The reactor vessel, steam generators, control systems, and shielding materials required specialized heavy-lift equipment capable of traversing ice fields while carrying enormous loads. Military engineers used massive tracked vehicles pulling cargo sleds designed to distribute weight across thin ice sections that might collapse under concentrated loads. The convoy operations required careful route planning to avoid crevasses and unstable ice formations, while weather monitoring prevented equipment from being caught in blizzards that could bury reactor components for months. Installation teams assembled the reactor components in underground chambers carved specifically to house the nuclear plant. The facility required sophisticated ventilation systems to remove radioactive gases while maintaining proper air circulation for personnel safety. Cooling water systems used heated pipes to prevent freezing while circulating water through the reactor core and heat exchangers. Control rod mechanisms needed special lubricants and heating systems to operate reliably in extreme cold, while instrumentation required constant calibration to account for temperature effects on sensitive measurement equipment. The reactor's first startup operations revealed immediate problems that sent radiation alarms screaming throughout the facility. Neutron radiation levels exceeded safe limits by factors that forced emergency shutdown procedures and evacuation of nearby areas. The reactor vessel produced excessive neutron flux that penetrated standard shielding materials, creating dangerous radiation exposure risks for personnel working in adjacent areas. Control room operators detected radiation readings that far exceeded design specifications, indicating fundamental problems with the shielding configuration and reactor physics calculation. Emergency radiation protection required improvised solutions using whatever materials were available at the remote Arctic location. Personnel constructed additional shielding barriers using lead sheets normally used for construction projects, while maintenance crews filled empty fuel drums with ice and sawdust to create makeshift neutron absorbers. These crude radiation shields provided temporary protection, but required constant monitoring and adjustment as ice melted and settled, creating gaps that allowed radiation leakage. Ongoing safety problems plagued reactor operations throughout its brief operational period. Radioactive leaks contaminated cooling water systems with isotopes that created disposal problems in the pristine Arctic environment. The reactor produced transmuted isotopes from neutron activation of structural materials, creating radioactive contamination in components that were originally clean. Contaminated cooling water couldn't be released into the surrounding ice without creating environmental hazards, while radioactive waste storage presented challenges in an environment where burial was impossible and transportation was limited to brief summer shipping season. The constantly shifting ice created structural problems that threatened reactor safety and operational reliability. Ice movement caused the reactor building ceiling to drop 1.5 meters over just a few years of operation, creating stress on reactor components and piping systems that weren't designed for such deformation. The settling ice compressed reactor building structures while creating uneven forces that threatened to damage critical systems. Foundation settlements affected alignment of reactor components and created new vibration patterns that stressed equipment beyond design limits. Personnel radiation exposure became a serious concern as reactor problems accumulated over time. Workers required extensive radiation monitoring while performing maintenance operations on contaminated systems. The improvised shielding systems provided inconsistent protection that left some areas with dangerous radiation levels, while personnel working in these areas accumulated radiation doses that exceeded recommended safety limits. Medical monitoring revealed elevated radiation exposure among reactor personnel, raising concerns about long-term health effects from working in contaminated environments. The reactor operated for less than 3 years instead of the planned 10-year operational period, proving that nuclear power in shifting ice environments was far more dangerous and unreliable than anticipated. Technical problems, safety concerns, and maintenance requirements exceeded the capabilities of personnel trained for conventional reactor operation. The constant need for repairs, radiation monitoring, and improvised safety measures consumed resources that should have been devoted to the facility's primary mission. The nuclear reactor experiment at Camp Century demonstrated that atomic power wasn't suitable for polar military installations despite theoretical advantages. The combination of extreme environmental conditions, structural instability, and radiation safety challenges created problems that couldn't be solved with existing technology. But the reactor's problems were just the beginning of a much larger crisis that would threaten the entire project. The engineers had made a fundamental miscalculation about their construction material that would prove far more dangerous than any radiation. When ice becomes your enemy, the ice itself had become the enemy. Engineers learned too late that glacial ice wasn't the rock-solid foundation they had imagined, but a constantly moving, unpredictable mass that followed its own rules. The Greenland Ice Cap moved continuously under its own enormous weight, flowing like an incredibly slow river that deformed everything in its path. What appeared stable from the surface concealed a dynamic system where ice layers compressed, shifted, and cracked without warning. Military planners had assumed they were building on permanent frozen ground, but they discovered they were actually constructing inside a living geological system that never stopped changing. The sewage crisis became the most immediate and disgusting reminder of ice's treacherous nature. Camp Century's waste disposal system relied on conventional septic methods that worked perfectly well in normal soil conditions. Engineers installed standard sewage processing equipment, assuming that frozen ground would contain waste products just like conventional installations. The reality proved far more nauseating than anyone anticipated. Raw sewage began percolating through the ice structure, following cracks and fissures that carried human waste throughout the underground complex. Within months, the entire facility reeked with an unbearable stench that penetrated every tunnel and living space. Personnel complained constantly about the smell, which became so overwhelming that some areas became unusable. The odor problem wasn't just unpleasant, but created serious health hazards as contaminated water supplies threatened drinking systems and food preparation areas. Maintenance crews struggled to locate the source of contamination as sewage followed unpredictable paths through ice formations, appearing in unexpected locations far from the original disposal sites. The sewage contamination revealed a fundamental misunderstanding about ice behavior that had catastrophic implications for larger installations. Ice wasn't impermeable like concrete or bedrock, but contained countless microscopic channels and fissures that allowed liquids to migrate throughout the structure. What seemed like solid barriers actually provided pathways for contamination to spread across enormous distances. The discovery meant that any large-scale facility would face similar contamination problems, potentially affecting thousands of personnel across kilometers of tunnel networks. Structural problems emerged as the constantly shifting ice warped tunnel sections and threatened the integrity of the entire underground complex. Ice movement created stress patterns that conventional construction materials couldn't handle. Metal framework designed for stable foundations began buckling and twisting as ice flowed around tunnel structures. Support beams developed stress fractures while ceiling panels sagged under uneven pressure loads. Tunnel walls showed cracks that widened daily as ice continued its relentless movement. The corrugated metal ceiling systems installed throughout Camp Century provided dramatic evidence of ice's destructive power. These panels, designed to flex with minor movement, couldn't accommodate the massive deformation forces generated by flowing ice. Ceiling heights decreased visibly as ice compressed from above, while floor levels rose as ice flowed underneath foundation systems. Some tunnel sections experienced compression forces that reduced their height by over 1 meter, making them impassable for vehicles and dangerous for personnel. Rail line construction for the mobile missile system would have faced impossible challenges from ice deformation. Track sections required precise alignment to allow trains to operate safely, but ice movement created constant changes in elevation and direction that would have made rail operations impossible. Switches and junction points needed exact positioning to function properly, but ice flow would have twisted these critical components out of alignment within months. The rail network would have required constant reconstruction, as ice movement destroyed track sections faster than crews could repair them. Maintenance operations consumed increasing amounts of time and resources as ice continued attacking the facility's infrastructure. Work crews spent most of their effort just keeping existing tunnels operational rather than expanding or improving the installation. Daily inspections revealed new damage from ice movement that required immediate attention to prevent catastrophic failures. Heating systems worked overtime to prevent ice from crushing tunnel structures, while drainage systems struggled to handle water from melting and refreezing cycles that created additional stress on building materials. Equipment failures multiplied as ice movement subjected machinery to forces far beyond design specifications. Generators developed vibration problems as ice shifted their mounting foundations, while ventilation systems suffered damage from tunnel deformation that misaligned ductwork connections. Communication equipment failed regularly as ice movement stressed cables and damaged connection points. Even simple fixtures like lighting systems required constant adjustment as tunnel deformation changed their mounting positions and electrical connection. The implications for nuclear materials storage became terrifyingly clear as structural problems worsened. Radioactive materials required stable storage conditions to prevent containment failures that could create environmental disasters. Ice movement threatened to damage storage containers while creating pathways for radioactive contamination to spread throughout tunnel systems. The mobile missile system would have faced even greater dangers, with nuclear warheads subjected to constant mechanical stress from ice deformation that could potentially trigger accidental detonations or radioactive releases. Scaling these problems to the full 4,000-kilometer tunnel system revealed the impossible magnitude of the challenge facing Project ICEWORM. What seemed manageable in a small demonstration facility would have become catastrophic across the massive installation planned for operational deployment. Thousands of personnel would have faced constant dangers from structural failures, while the rail network would have required complete reconstruction every few years just to remain functional. The maintenance requirements alone would have consumed more resources than the entire military budget could provide. The ice that promised to hide America's ultimate weapon had become Project ICEWORM's ultimate destroyer, making long-term military operations impossible in an environment that never stopped trying to crush everything humans built within it. But even as engineers battled these seemingly insurmountable technical challenges, a far more dangerous threat was already developing thousands of kilometers away in the diplomatic corridors of Copenhagen and Washington. The political iceberg. Denmark's nuclear weapons ban had created a diplomatic minefield that threatened to destroy the entire project before construction could begin. The country had officially prohibited all nuclear weapons from Danish territory in 1957, including Greenland, which remained under Danish sovereignty despite American military access agreements. This created an impossible situation for American planners, who had already stationed nuclear weapons at Thule Air Base without informing Danish authorities of their true nature. The nuclear prohibition put American forces in an extremely awkward position. Strategic Air Command bombers had been carrying nuclear payloads during routine operations since the early 1950s, while ground-based nuclear weapons provided defensive capabilities against potential Soviet attacks on the strategically vital radar installation. American military commanders had interpreted their access agreements as providing sufficient authority for nuclear deployments without requiring specific permission for each weapon system. But Danish officials clearly disagreed with this interpretation. The diplomatic complications created a catch-22 situation that Pentagon planners couldn't resolve through normal channels. Asking Denmark for permission to deploy nuclear weapons would require acknowledging that America had already violated the 1957 ban by maintaining existing nuclear arsenals on Greenlandic territory. Such revelations would create a major diplomatic incident that could damage NATO alliance relationships and potentially force the removal of all American nuclear assets from the strategically crucial Arctic location. American diplomats found themselves walking a tightrope between military requirements and alliance politics. NATO nuclear sharing arrangements were becoming increasingly controversial as European allies demanded greater control over nuclear weapons stationed on their territory. The Jupiter missiles in Turkey and Italy had created similar diplomatic headaches when host governments began questioning American control over weapons that could trigger nuclear war without their consent. Greenland represented an even more sensitive situation because Danish officials had explicitly prohibited nuclear weapons, while American military leaders considered them essential for Arctic defense strategies. Inter-service rivalry added another layer of political complexity to Project ICEWORM's approval process. The Navy's multilateral force program promised to address NATO nuclear sharing concerns by deploying submarine-launched missiles with mixed international crews, giving European allies direct participation in nuclear operations. This competing program offered similar strategic advantages to ICEWORM while addressing diplomatic concerns about host nation approval and alliance consultation. Navy officials argued that submarine-based missiles provided better survivability and flexibility than fixed ice installations, while avoiding the political complications of land-based deployments on foreign territory. The Army faced increasing pressure to justify Project ICEWORM's enormous costs and diplomatic risks when alternative solutions seemed more politically feasible. Military budget battles intensified as different services competed for nuclear mission assignments and funding allocation. The Navy's submarine program had strong support from Defense Secretary Robert McNamara, who preferred flexible response strategies over massive retaliation doctrines that required large numbers of land-based missiles. Congressional appropriations committees questioned the wisdom of investing billions in ice installations when submarine technology offered similar capabilities without diplomatic complication. Project ICEWORM's classification requirements created additional political obstacles that prevented open discussion of the project's strategic benefits. Military planners couldn't publicly explain why Greenland installations were superior to submarine-based alternatives without revealing operational details that would compromise the project's security. The cover story about peaceful scientific research provided plausible explanations for Camp Century's activities, but couldn't justify the massive investments required for the full-scale installation without raising questions about the project's true purpose. Congressional oversight became increasingly difficult to manage as Project ICEWORM's costs escalated without visible progress toward operational deployment. Appropriations committees demanded detailed explanations for budget requests that military officials couldn't provide without revealing classified information about nuclear weapons deployment. The scientific research cover story satisfied initial congressional inquiries, but couldn't explain why Arctic research required such enormous investments in construction equipment and infrastructure development. The lack of official Danish approval created legal vulnerabilities that could have exposed the entire project to political attack. International law required host nation consent for nuclear weapons deployments, while NATO alliance agreements specified consultation procedures for nuclear operations that could affect alliance members. Project ICEWORM violated both requirements by deploying nuclear weapons without Danish permission and planning nuclear operations without NATO consultation. The 1968 nuclear bomber crash at Thule Air Base provided a dramatic example of how nuclear secrecy could create diplomatic disasters. A B-52 bomber carrying 4 nuclear weapons crashed and burned on the ice near the base, scattering radioactive materials across the Arctic landscape and revealing the extent of American nuclear operations in Greenland. Danish officials expressed outrage at discovering the scale of nuclear weapons deployments that had been conducted without their knowledge or consent, creating exactly the kind of diplomatic crisis that Project ICEWORM's secrecy was designed to prevent. The bomber crash exposed the fundamental contradiction at the heart of Project ICEWORM's political strategy. The project's security requirements made it impossible to obtain the political approvals necessary for legal deployment, while the diplomatic risks of unauthorized nuclear operations threatened to damage alliance relationships that were essential for the project's strategic success. Military planners had created a weapons system that was too secret to deploy legally but too important to abandon, trapping themselves in a political maze with no acceptable exit strategy. By 1967, the combination of technical failures, diplomatic obstacles, and escalating costs had made Project ICEWORM's continuation impossible to justify. The $26 billion failure. The Pentagon's decision to terminate the project triggered a financial reckoning that still defies comprehension. The Army had spent $2.37 billion in 1960s dollars on this failed Arctic adventure, which translates to approximately $26 billion in current purchasing power. To put that staggering sum in perspective, it exceeded the entire annual budget of many federal agencies and could have funded NASA's early space program for several years. The money vanished into the Greenland ice with nothing to show for it, except a contaminated hole in the ground and hard lessons about the limits of military engineering ambition. Military planners made the painful decision to abandon Camp Century in 1967 after just 8 years of increasingly problematic operations. The facility that was supposed to demonstrate the feasibility of massive ice installations had instead proven that such projects were financial black holes that consumed resources without delivering practical military capability. Equipment failures, structural problems, and safety concerns had turned the demonstration base into a constant drain on military budgets, without producing any of the strategic advantages that justified the enormous investment. The evacuation resembled a military retreat more than an orderly base closure. Personnel packed only essential items and personal belongings while leaving behind most of the equipment and infrastructure that had cost millions to transport and install. The nuclear reactor required careful decommissioning procedures, but other systems were simply abandoned in place. Heating equipment, construction machinery, communication systems, and living facilities were left to be gradually buried by accumulating snow and ice. The hasty departure reflected military leadership's desire to cut losses and avoid throwing good money after bad on a project that had clearly failed. What remained buried in the ice created an environmental time bomb that would haunt military planners for decades. The abandoned facility contained approximately 200,000 liters of diesel fuel stored in underground tanks that were never properly emptied or removed. This massive quantity of petroleum products sat frozen in the ice, alongside hydraulic fluids, lubricating oils, and other petroleum-based materials used throughout the facility. Chemical waste from maintenance operations included solvents, cleaning agents, and industrial chemicals that had been disposed of using methods that seemed appropriate for permanent ice storage. The sewage contamination problem that had plagued Camp Century's final years left behind an estimated 24 million liters of untreated human waste distributed throughout the ice structure. This biological contamination had spread far beyond the original disposal sites, following ice fractures and melt channels that carried sewage throughout the tunnel system. The waste included not just human sewage, but also gray water from kitchen operations, laundry facilities, and cleaning activities that contained detergents and other chemicals harmful to Arctic ecosystems. Radioactive contamination from the troubled nuclear reactor presented the most serious long-term environmental threat. The reactor had leaked approximately 1.2 gigabecquerels of radioactive cooling water into the surrounding ice during its brief operational period. Contaminated components and radioactive waste from reactor maintenance operations were left behind when the facility closed. The radioactive materials included activated metals from reactor components, contaminated tools and equipment, and low-level radioactive waste that had accumulated during 3 years of problematic reactor operations. Military planners assumed that the Greenland ice sheet would provide permanent storage for the contaminated materials left behind at Camp Century. The ice cap appeared stable and permanent, with accumulating snow gradually burying the abandoned facility deeper each year. Scientists calculated that the contaminated site would remain frozen for thousands of years, effectively isolating dangerous materials from the environment and human contact. This assumption seemed reasonable given the apparent stability of the Greenland ice sheet and the remote location that made accidental human exposure unlikely. The true purpose of Project ICEWORM remained classified for 30 years after Camp Century's abandonment. In 1997, declassified documents finally revealed that the facility had been designed as a demonstration project for a massive mobile nuclear missile system, rather than the peaceful scientific research station described in public statements. The revelation shocked Danish officials who had never been informed of the military purpose behind American activities on Greenlandic territory. Environmental groups expressed outrage at discovering the extent of contamination left behind by military operations conducted under the cover of scientific research. Personnel who worked at Camp Century faced serious health consequences from radiation exposure and other occupational hazards associated with the facility's operations. Many reactor technicians and maintenance workers received radiation doses that exceeded recommended safety limits due to inadequate shielding and emergency repair operations on contaminated equipment. Medical monitoring revealed elevated cancer rates and other health problems among Camp Century veterans that suggested long-term effects from radiation exposure and chemical contamination during their Arctic service. The failure of Project ICEWORM fundamentally changed American approaches to Arctic military strategy and polar construction projects. Military planners abandoned plans for large-scale permanent installations in ice environments, recognizing that the technical challenges and environmental risks exceeded the strategic benefits. Future Arctic military operations would rely on smaller, temporary facilities that could be easily removed without leaving behind contaminated site. Project ICEWORM stands as one of the Cold War's most expensive failures, consuming enormous resources while producing no useful military capabilities. The underground nuclear fortress that was supposed to guarantee American strategic superiority instead became a cautionary tale about the limits of military technology and the dangers of pursuing ambitious projects without adequate understanding of environmental consequences. Yet the strategic vision that drove this massive undertaking would prove remarkably prescient, as global powers today recognize what American planners understood 6 decades ago about the Arctic's military importance.